morning, everyone. I'm Sahil Ramlogan, and today I will be presenting my paper on semi-automated cricket broadcast highlight generation. Over the past 3 decades, increased revenue within professional sports has caused it to develop into a big business. One of the major changes afforded by this is the use of data science and analytics to win games. It allows coaches to operate more efficiently, providing instantaneous feedback and correction. In particular, video analysis technologies are the key to more effective practices, scouting, injury prevention, and breaking down games. Coaches can use these videos to show them their progress when they are making any correction and prevent injuries by correcting bad forming technique. In cricket, using video analysis means that specific scenes must be picked out from full match broadcasts. Typically, these key points lie within 10% of a 4 to 5 hour long video. Therefore, extracting these key points is time consuming and costly. My paper seeks to address this issue within the sport of cricket using the following objectives. Firstly, to determine what is happening for each delivery, we will be extracting the metadata from text commentary. To determine the beginning of a delivery, we must detect the bowler run-up sequence, or the BRS. Each delivery must then be paired with the relevant metadata to make them easily searchable for the user. The quality and accuracy of the implementation is then compared and assessed, and the final system performance is also assessed. To achieve these objectives, the following design was adopted. The solution was formed by dividing it into 3 separate parts: a commentary extraction component, the BRS Identification and Extraction component, and finally the automated video and metadata compiler, which utilized the outputs of the previous 2 components to automatically create a searchable database. We can now discuss what the design was for each of these components separately. The first component, the commentary extractor, was designed in Python using the Beautiful Soup library. Component utilized the fact that the detailed commentary for each delivery in a cricket match is available via various cricket websites. The URL for the match or series that the commentary was needed from was provided to the program. This program would then copy the relevant text commentary to a text file, which is appropriately stored and named according to the match and the series or tournament name. This component is known as the BRS Identification Extraction component, and it analyzes video footage from 1 innings of a match. 6 trained frames must be provided, covering each type of bowler and each type of batsman. Since teams in T20 cricket wear different colored clothing, the training must be redone for each innings. Examples of these are seen here and include a spinner and a pace bowler around the wicket to a right-hand batsman, a spin bowler and a pace bowler over the wicket to a right-handed batsman, and pace bowlers over and around the wicket to a left-handed batsman. The orb function is applied to these frames, and the key points and descriptors for each are extracted. Frame-by-frame analysis is conducted on the imported video by applying the orb function to each video frame and then comparing the key points and descriptors of each frame to the training frames. If these match within a set threshold, the frame is determined to be a BRS match. Consecutive BRS matches constitutes a valid candidate to be recorded. A user refinement phase is implemented to eliminate the occurrence of false positives. The final output is recorded and stored into a file to be accessed in a later component. These videos are named so that they maintain a chronological order. The videos from the previous component are imported, and relevant commentary file is also imported. The pattern found in commentary text are taken advantage of to extract the information needed to fill each of the table columns. As seen here, these include the bowler and batsman names, delivery, and event for each delivery. Each line of text is equivalent to one record within the database, and each record contains one video. The commentary is stored in chronological order. Given that the commentary and videos are both in chronological order, it is assumed that the first video file will correspond to the first database record. Therefore, each database record will have a corresponding video file address. The GUI for the database was done in C# using MySQL to create and control records within the database. The GUI was designed to allow a user to either view the full database or set parameters within which he or she would like to search. For example, someone could search for a specific bowler or batsman to see what that player has done within the match, or you can search specific events within a match, such as all the fours hit or even a combination of these factors. The user can then click on the video column of an entry in order to see the corresponding event. On this slide, we can see the key point matches that have been picked out by the orb according to the parameters that were set. The significant key points in this example lie on the batsman and the umpire. This slide shows an example of how videos are stored after the BRS extraction is done. As you can see here, each delivery is stored and labeled in a manner to preserve the sequence of events within a match. During the testing phase, the algorithm was run in 5 different ways on one innings of a T20 match. First, one training frame was used to try to identify the BRS. When this produced an accuracy of 46.8% with a false match rate of 37%, a test was set up to determine whether varying the side of the umpire that the bowler was running in from was a factor. Therefore, 2 training frames were used. This increased the accuracy but also the false match rate. Therefore, a 6th training frame test was conducted that also increased the number of consecutively matched frames required to give a positive match. This method raised the accuracy to 96.8% and decreased the false match rate to 38%. A further refinement was done to the 6th training frame technique that checked for multiple positive matches across the training frames, resulting in a drop in the false match rate. Also, the number of consecutive matches needed was slightly reduced from the previous test, producing a more accurate algorithm. To eliminate false match data, a user verification component was introduced. This resulted in a 97.5% accuracy for the first innings with a 0% false match rate. After providing new training frames for the second innings, the algorithm was run again with 98.3% accuracy. Okay, I will now give a short demo of the database part of this paper. When we run the program, this is the first menu that is seen. If I click on the View or Search Database button, we can see that it is empty. So, let us go back to the main menu and import our data. So if I click on this button, you can see we have a menu here. Right, let us first add the folder containing the BRS video matches. So it's the first innings here, select that. And now the commentary file. Since these BRS videos are for the first innings of this match, we'll enter one here and a generic ID, match ID. We are not exactly sure of the stadium, so we'll leave that blank. Click the import button and the videos have now been imported. So let's view the database. So if we take a look at the database here, we can see we have all the information that is necessary. We have the delivery, the bowler, the batsman, and what the event is. If I click the video address here, we'll be able to see the event for that specific database entry. Okay, so now if we want to see something more specific, let's say all the 4s hit by M Pandey. We can enter that information here. All the 4s and hit search, right? And then if we click again on the video, we can see this is 1-4 here. Right, and we can see from the information here, right, it's Corey Anderson, and for this this second entry here, Harbhajan Singh is the bowler. Right, let's take a look again. And you can see that's another 4 hit there. Let's say, for example, you would like to take a look at the wickets taken by Malinga, let's say. Can enter that information here, and we take a look at this second entry here. Now we can see it's Malinga to Gambhir, and he's out. Right. So based on this, we can see how useful this information is, right? And it allows people or the user to find and look at different things that happen within a match, right? And extract only what is relevant and what is needed, right? Another example here is like a 6. If you want to see the strengths of Pandey where you're bowling and you want to change your line, right? You don't want to be bowling there to him because you know he'll hit you for 6. Now that we've seen this demo, we'll now take a look at the problems encountered while conducting this research. One of these problems included, during the BRS identification stage, there was transitions between deliveries. These transitions are used to show short highlights from within the match and sometimes return to the live action late. This usually happens when spin bowlers are bowling. As a result, the number of consecutive matches to constitute a valid candidate for a BRS match could not be obtained, and this can result in missed BRS detection. This in turn leads to another problem with this design. When these deliveries are missed, it causes the commentary data and videos to be out of sync when being stored in the database. A suggestion for future improvements would be to account for the missing BRS segments. This graph shows the intervals between deliveries for the first innings of a T20 match. This shows that the average time between deliveries is 30 to 45 seconds. The spikes in the graph generally indicate major events such as boundaries, wickets, or the transition between overs. Using this knowledge of time intervals in conjunction with the commentary information, the location of the missing BRS videos can be approximated. Another way to improve this algorithm would be with regards to the processing time. As the processing time right now runs at about 1.5 times the speed of the video itself. Therefore, introducing parallel processing would be an effective way of increasing the processing speed of a video. This concludes my presentation, and I would like to thank you all for your time today.
Thank you very much, Sahil. Thank you very much. I must say it has reignited some hope for West Indies cricket there, right? And let me just jump straight into 2 questions I'm seeing online here. So the first one, Sahil, can you share some insight into the training between innings, for instance, the timing required and the requirements of the dataset?
Okay, you all can hear me fine, right?
Yes, we can.
Okay, so the main thing with the training, and well, one of the problems that we encountered is that we have to slightly go through the actual innings itself, right? And pick out, like, for example, those 6 frames that I explained, where we have different scenarios within the match, right? Because sometimes because of the variance in the run up for the bowlers and the variance in the direction that the batsman is facing, it gives us a problem in terms of being able to identify the BRS and get positive matches, right? So that's why I had to introduce those different frames, right? And the timing between innings is actually not that bad, because as long as you could quickly find those frames, those reference frames, the orb itself simply, you provided those frames and it will be able to match those frames against the frames within the video, right? So the training time itself is non-existent, I would say.
Okay, so I guess that would also be true if it's for a test match. You'll probably have to have a lot more frames then.
Well, the thing about it is that for a test match, because one, they're all wearing white, right? And then the second thing is that you would have, okay, so effectively the scenarios you would have is it would be basically the same, right? So you wouldn't have to retrain between innings. At that point, it will be simple. Once you have your scenarios, because they all wear the same color, you're gonna have you're gonna be able to go straight through and identify for the test match.
Okay, all right, thanks for that.
Yeah.
I have another question here. Are you working with any threshold value for false match rate?
Well, if is in reference to how we ended up eliminating the false match rate, then what we did is we set a hard threshold, whether it was a yes or a no for the for a false match or not.
Okay.
And that was in the that in the refinement phase, right? There wasn't really any threshold itself, but we introduced that when we did the introduction for the user to be able to interact.
Okay, good.
Yeah.
All right. Well, thank you very much.